Saturn is the most beautiful object in the solar system. This is not a subjective, aesthetic judgment. It is the most consistent reaction reported by every astronomer who has pointed a telescope at it for the first time, by every space mission operator who has seen the first images returned from its vicinity, by everyone who has had the experience of resolving that ring system against the black sky through an eyepiece. The rings, the bands, the hexagonal storm at the North Pole, the moons visible as tiny points of light in precise orbital arrangement. Saturn looks like something that was designed, something too geometrically perfect and too visually striking to have simply happened. It happened. 4.5 billion years of physics produced it without intention or design, and it is extraordinary. But Saturn is not beautiful in the way that a sunset is beautiful, something you can walk into, something whose warmth you can feel, something that can be experienced through the body as well as the eyes. Saturn is beautiful the way a star is beautiful, remotely, visually, across a distance that makes physical engagement essentially impossible. Saturn is 1.2 billion kilometers from the Sun at its closest approach. It is 1.4 billion kilometers from Earth on average, and up to 1.7 billion kilometers at its farthest. The light you see when you look at Saturn in the night sky left it approximately 80 minutes ago. And if a human being were to attempt to travel there, to actually go to Saturn in the physical sense, to make the journey from Earth to the vicinity of that ringed world, the journey would almost certainly be one way. Not because of any single catastrophic risk, not because of any obvious single point of failure, but because of the accumulation of specific physical realities that make a return journey from Saturn to Earth so demanding that it pushes against the limits of what any foreseeable human mission could achieve. Tonight, we are going to examine these specific physical realities one by one, not to argue that Saturn is unreachable. It is reachable, at least for robotic spacecraft, and the history of Saturn exploration includes some of the most successful and scientifically productive missions ever flown. But to argue that the specific combination of distance, radiation, transit time, physiological cost, and return propulsion requirements makes human travel to Saturn and return to Earth a genuinely different category of challenge from anything attempted in the history of human spaceflight. A challenge that, at current and near-future technology levels, does not have a clear solution. Before we begin, if you put this on because the night is long and you want something to settle into, stay. What follows is the honest physics of one of the most extreme journeys any human being has ever considered making. Let us start with the distance. Because the distance to Saturn is the foundational constraint from which all others flow, and the distance is genuinely hard to internalize at human scales, 1.4 billion kilometers. This is the average Earth-Saturn distance. Let us make this number real. Light, the fastest thing in the universe, traveling at 299,792 kilometers per second, takes approximately 80 minutes to travel from Saturn to Earth. A radio signal, a phone call, a command from mission control, any electromagnetic communication with a spacecraft at Saturn takes 80 minutes to arrive. The response takes another 80 minutes to return. A simple question and answer exchange takes almost 3 hours. Real-time communication in any meaningful sense is impossible. The crew of a Saturn mission would be completely on their own for all practical purposes, unable to consult with Earth in any situation requiring rapid response. The fastest human-made object that has travelled to Saturn, the Cassini spacecraft, which reached Saturn in 2004, took approximately 6.7 years to get there. It did so using a complex series of gravitational assist maneuvers, flying past Venus twice, Earth once, and Jupiter once to build up enough velocity to reach Saturn within a reasonable time frame. A direct trajectory from Earth to Saturn without gravitational assists would take longer and require more fuel. Even with the most favorable gravitational assists and the most efficient trajectories available with current propulsion technology, a crewed mission to Saturn would take approximately 3 to 6 years in transit each way. That is 3 to 6 years of continuous spaceflight just to reach the destination, before any time spent in the Saturn system, before any time spent returning. The total mission duration, outbound transit, operations at Saturn, return transit, would be measured in decades, not years, decades. To put this in context, the longest continuous spaceflight ever completed by a human being is approximately 437 days, just over 14 months, by cosmonaut Valery Polyakov on the Russian Mir space station in 1994 to 1995. The longest cumulative time spent in space by any individual is approximately 878 days by cosmonaut Oleg Kononenko. The longest planned NASA mission is currently approximately 1 year on the International Space Station. A Saturn mission would require human beings to survive in deep space for a period approximately 10 to 20 times longer than the longest spaceflight ever attempted. Every physiological, psychological, and engineering challenge that makes long-duration spaceflight difficult would be present, and would be present for a duration for which we have no experience, no data, and no tested countermeasures. Let us be specific about what those challenges are. The first is radiation. The Earth's magnetic field, generated by the dynamo in its fluid outer core, creates a magnetosphere that deflects the majority of the solar wind and a significant fraction of galactic cosmic rays. The International Space Station orbits within this protective field at an altitude of approximately 400 kilometers. Astronauts on the ISS receive a radiation dose of approximately 1 millisievert per day, roughly equivalent to receiving a chest X-ray every single day. This is elevated compared to Earth's surface radiation levels, but manageable for stays of up to a year. Beyond the Earth's magnetosphere, the radiation environment changes dramatically. In interplanetary space, the space through which a Saturn-bound spacecraft would travel for years, astronauts are exposed to 2 primary radiation sources. The solar wind, the continuous stream of protons and electrons from the Sun, delivers a relatively steady but manageable background dose. Solar energetic particle events, the intense bursts of high-energy particles produced by solar flares and coronal mass ejections, can deliver an acute high dose over a period of hours to days. In interplanetary space, the dose rate from galactic cosmic rays, high-energy particles from outside the solar system, is approximately 1.8 millisieverts per day. Over a 6-year transit to Saturn, this amounts to approximately 3.9 sieverts of galactic cosmic ray dose alone, before accounting for solar energetic particle events. The NASA career limit for astronaut radiation exposure is 1 sievert, meaning a Saturn transit would expose crew members to approximately 4 times their career limit just from background cosmic rays. The specific biological concern with galactic cosmic rays goes beyond the total dose. Galactic cosmic rays include heavy ions, nuclei of elements like carbon, oxygen, iron, and lead stripped of their electrons and accelerated to near-light speeds. These heavy ions produce dense ionization tracks as they pass through tissue, damaging DNA and creating clusters of damage that are particularly difficult for cells to repair. The biological effectiveness of heavy ion radiation is significantly higher than for lower LiT, linear energy transfer radiation, like gamma rays. The risk of cancer, cataracts, and central nervous system damage from heavy ion exposure over years of interplanetary transit is not well quantified, because no human has experienced this exposure for such a duration. The shielding problem for galactic cosmic rays is severe. Unlike solar energetic particles, which can be largely blocked by relatively modest shielding, water, polyethylene, or other hydrogen-rich materials, galactic cosmic rays are so energetic that adding more shielding can actually make things worse by producing secondary particle showers. The optimal shielding for galactic cosmic rays is thin, not thick, because each interaction of a primary cosmic ray with a shielding nucleus produces a cascade of secondary particles that can deliver more dose than the primary would have if it had passed through unobstructed. There is no practical amount of shielding that can protect a crew from galactic cosmic ray exposure on a multi-year interplanetary transit. The physics simply does not allow it, with any material we know of at any practical mass. This is the radiation problem. It is not a problem that better engineering can solve within known physics. It is a constraint imposed by the fundamental properties of high-energy particles and matter. The second major challenge is the physiological effect of microgravity. In the absence of gravity, or in the near weightlessness of freefall during interplanetary transit, the human body undergoes systematic deterioration across multiple organ systems. Bone loss is the most well documented. In microgravity weight-bearing bones, the spine, the hips, the legs, lose mineral density at a rate of approximately 1 to 1.5% per month. Over 6 months, this amounts to 6 to 9% loss, a degree of bone loss that would take decades to develop through normal osteoporosis on Earth. Over 6 years of transit to Saturn, this would amount to 70 to 100% loss of bone mineral density in weight-bearing bones, far beyond any level compatible with functional mobility after return to gravity. Exercise mitigates but does not eliminate this bone loss. The ISS exercise protocol, approximately 2 hours per day of resistance and aerobic exercise, reduces bone loss substantially, but does not prevent it entirely. 6 months of rigorous ISS standard exercise leaves most astronauts with measurable bone density reductions that require months to years of rehabilitation after return to Earth. 6 years of exercise in microgravity, even with the most advanced exercise protocols, would likely produce bone loss that is irreversible in practice, even if not in principle. Muscle loss occurs in parallel. Without the constant load of supporting body weight against gravity, muscles atrophy despite exercise. The specific muscles of the lower extremities, the quadriceps, hamstrings, calf muscles, deteriorate most severely because they are most dependent on gravitational loading in normal Earth use. After 6 months in microgravity, astronauts return to Earth with significant lower body weakness that requires months of rehabilitation. After years, the deterioration would be more severe and potentially permanent. Cardiovascular deconditioning is another systematic effect. The heart adapts to the reduced workload of microgravity by becoming smaller and less efficient. Blood pressure regulation, which depends on the cardiovascular system maintaining appropriate pressure against the pull of gravity, deteriorates. Orthostatic hypotension, dizziness and fainting when standing up, is a common problem for returning astronauts who have been in microgravity for months. After years, the cardiovascular deconditioning would be severe, and the functional capacity upon return to Earth's gravity, if a return occurred, would be substantially reduced. Vision impairment from spaceflight-associated neuroocular syndrome, SANS, is a growing concern. Approximately 70% of astronauts on long-duration ISS missions develop some degree of visual impairment. The mechanism involves the redistribution of fluids toward the head in microgravity, which, in the absence of gravity's normal downward pull, causes fluid to accumulate in the upper body and head. This increased intracranial pressure can damage the optic nerve, cause retinal changes, and alter the shape of the eyeball. Some of these changes are permanent. Over years of microgravity exposure, the cumulative damage could be severe. These are the effects of current microgravity exposure durations. Extrapolating to years, the duration required for a Saturn transit, involves significant uncertainty because no human has spent years in microgravity, and the relationship between exposure duration and physiological damage may not be linear. Some effects may plateau, others may continue to accumulate. Some may become irreversible at durations beyond what we have studied. The solution most commonly proposed for the microgravity problem is artificial gravity, rotating sections of the spacecraft that create centripetal acceleration equivalent to some fraction of Earth's gravity. This is physically straightforward in principle. A rotating habitat produces effective gravity, but presents significant engineering challenges. The rotation rate must be high enough to produce useful gravity within a habitat of reasonable size, but rotation rates above approximately 2 to 4 revolutions per minute produce Coriolis effects that cause disorientation and motion sickness. Producing 1g at 2 revolutions per minute requires a rotation radius of approximately 224 meters, a habitat 224 meters from the rotation axis. This is a very large structure by any current spacecraft standard. No spacecraft with artificial gravity has ever been built and flown. The engineering challenges are not insurmountable. They are well understood in principle, but they are substantial and have never been confronted in practice. A Saturn mission spacecraft with adequate artificial gravity would be dramatically larger and more complex than any spacecraft ever built. The mass required and the cost of launching that mass to the required trajectory would be extraordinary. Let us now talk about the propulsion requirements, because the specific physics of travelling from Earth to Saturn and back determines what is and is not achievable in terms of the return journey. The fundamental unit of propulsion analysis in spaceflight is delta V, the change in velocity required to perform a given manoeuvre. Every trajectory adjustment, every orbit insertion, every return burn requires a specific delta V that must be provided by burning propellant. The Tsiolkovsky rocket equation relates the delta V achievable to the mass of propellant carried and the exhaust velocity of the propellant. The higher the exhaust velocity and the higher the propellant fraction, the higher the achievable delta V. The total delta V required for a round trip from Earth orbit to Saturn orbit and back to Earth is enormous. A rough estimate for a fast transit, minimizing the time spent in transit at the cost of more propellant, requires approximately 8 to 10 kilometers per second to depart Earth orbit. Additional delta V for Saturn orbit insertion on arrival, additional delta V for departure from Saturn, and additional delta V for Earth orbit insertion on return. The total delta-V requirement for a crewed round trip is on the order of 15 to 25 kilometers per second, depending on the specific trajectory. Current chemical propulsion, the most powerful propulsion technology that has been actually used in spaceflight, has a maximum exhaust velocity of approximately 4.4 kilometers per second for the most efficient propellants, liquid hydrogen and liquid oxygen. To achieve 20 kilometers per second of delta-V with chemical propulsion starting from Earth orbit requires a mass ratio, the ratio of total initial mass to final dry mass, of approximately e to the power of 20 over 4.4, approximately e to the 4.5, approximately 90. This means the spacecraft must be 90 times heavier at departure than it is after the propellant is burned. For a crewed spacecraft that must carry life support, food, water, exercise equipment, scientific instruments, and habitat for years, a dry mass of perhaps 50 to 100 metric tons would be a minimum. The required initial propellant mass would be approximately 4,500 to 9,000 metric tons. This is simply not achievable with current launch technology. The Saturn V, the most powerful rocket ever flown, could lift approximately 130 metric tons to low Earth orbit. Achieving the required mass in orbit would require dozens to hundreds of launches and in-orbit assembly of a scale never attempted. Nuclear thermal propulsion, using a nuclear reactor to heat propellant and expel it at higher exhaust velocity, would improve the exhaust velocity to approximately 8 to 9 kilometers per second. This reduces the required mass ratio dramatically from approximately 90 to approximately 10, making the mission more feasible in principle, though still enormously challenging in practice. Nuclear pulse propulsion, the Orion concept, in which a spacecraft is propelled by a series of nuclear explosions, could potentially achieve exhaust velocities of thousands of kilometers per second and make the Saturn transit in months rather than years. But nuclear pulse propulsion has never been built and tested in space, and political constraints on nuclear explosions in space under the Partial Test Ban Treaty make its near-term development unlikely. The key point is this: the return journey from Saturn to Earth requires as much propellant as the outbound journey. All that propellant must either be carried from Earth, adding enormously to the mass that must be launched, or produced in the Saturn system. There is no known resource in the Saturn system from which hydrogen-oxygen rocket propellant can be conveniently extracted. Saturn's atmosphere contains hydrogen, but extracting it and converting it to rocket propellant in the required quantities would require infrastructure that does not exist and could not be delivered within a reasonable mission timeline. This is the fundamental reason why anyone who goes to Saturn may never come back. Not because Saturn is actively hostile, not because there is some danger that prevents return, but because bringing back enough propellant to return to Earth, or producing it in the Saturn system, or developing propulsion technology efficient enough to make the return feasible, none of these options is available with current technology, or with any technology likely to be available in the near future. Let us talk about the psychological dimension of the Saturn mission, because the physiological challenges are severe, but the psychological challenges may be equally significant and are less well understood. Human beings evolved in environments with constant sensory input: changing weather, changing landscapes, diverse social groups, the cycle of day and night, the seasons, the presence of other species. The brain is not a passive recorder of experience, but an active prediction machine that requires novel input to function normally. It compares incoming sensory data to predictions built from past experience and generates signals of interest, curiosity, or alarm when the input deviates from prediction. In the featureless environment of interplanetary space, this system is starved. The view from a spacecraft window does not change day to day, week to week, month to month. The stars are in the same positions. The perspective shift from moving through the solar system is too small and too slow to be visible in real time. The interior of the spacecraft, the habitat module, the galley, the exercise area, the laboratory, are the same every day. The crew members are the same. The schedule is the same. The sensory environment is profoundly and continuously monotonous. The psychological response to this monotony is well documented from analog environments: Antarctic winter overstations, submarine patrols, isolated research facilities. What researchers call the third quarter phenomenon appears reliably in isolated confinement. A deterioration in mood, motivation, and interpersonal relationships that begins roughly 3/4 of the way through a known duration isolation period. The crew members know they are approaching the end, but feel that it is not approaching fast enough. Irritability increases, productivity decreases, interpersonal conflicts become more frequent and more difficult to resolve. For a Saturn mission, the third quarter phenomenon would operate on multi-year timescales. A 6-year outbound transit would produce a third quarter crisis approximately 4.5 years in, 4.5 years from Earth, still 1.5 years from Saturn, with the entire return journey ahead. The psychological burden at that point would be extraordinary. Beyond the monotony is the isolation from Earth. An 80-minute communication delay means no real-time conversation with family, friends, or support personnel. Messages are one way, sent and received with an hour and 20 minutes of silence on each side. The accumulation of events that happen on Earth during the years of transit, family members aging, friends moving through life, cultural and political changes, the passage of time, creates a growing sense of temporal displacement. The crew exists in one time, while Earth exists in another, and the two are increasingly out of sync. The research on how isolation affects human performance is not reassuring. Cognitive performance, reaction time, working memory, attention, deteriorates in extended isolation, even without the confounding factors of radiation, microgravity, and physical discomfort. Decision-making quality decreases. Risk assessment becomes less accurate. The ability to maintain perspective on small problems, to avoid catastrophizing minor irritants, diminishes. These cognitive effects would be present throughout the mission and would be most severe at the times when clear thinking is most critical: during emergencies, during complex operations at Saturn, during the return journey. The specific composition of the crew would be critical. Crew selection for a Saturn mission would need to identify individuals not just with the technical skills to operate the spacecraft and conduct the science, but with the psychological profiles that allow sustained, high performance in extreme isolation. The research on what those profiles look like is active but incomplete. The military and space agency programs that select for long-duration mission suitability use batteries of psychological testing and simulated isolation to identify candidates, but the duration and severity of conditions on a Saturn mission exceed anything the selection process has been validated against. Crew interpersonal dynamics on long-duration missions are one of the most consistently identified risk factors. In any small group confined in a small space for an extended period, interpersonal conflicts will develop. The question is not whether conflicts will occur, but how severe they will become, and whether the crew has the skills and the interpersonal resilience to manage them without permanent damage to the relationships that are required for the mission's success. On the ISS, crew members can be returned to Earth within hours in an emergency. The Soyuz serves as a lifeboat with a realistic return option. On a Saturn mission, there is no return option. Whatever conflict develops must be resolved within the crew, because there is no way out. The specific scenario of a crew member becoming incapacitated, through illness, through injury, through psychological breakdown, is one of the most challenging contingencies to plan for. On Earth, if a team member becomes unable to perform their duties, the team can be supplemented or replaced. On the ISS, crew members can be evacuated and replaced. On a Saturn mission, the crew that leaves Earth is the crew that arrives at Saturn, and the crew that returns, if a return happens. Losing a crew member to incapacity reduces the crew's total capability in ways that cannot be compensated for, and that may make the mission impossible to complete safely. Medical care is another dimension of the psychological challenge. The crew would need to provide all medical care to themselves and each other for the duration of the mission. There is no emergency evacuation to a hospital, no consultation with a specialist in real time given the communication delay, no access to sophisticated diagnostic equipment beyond what was carried from Earth. Crew members would need to be trained to a level of medical competence comparable to a physician, able to diagnose and treat a wide range of conditions, including surgical emergencies, using equipment compact enough to fit in a spacecraft and reliable enough to function for decades without servicing. Telemedicine, remote consultation with Earth-based physicians via video link, is possible, but the 80-minute delay makes it useless for acute emergencies. A crew member experiencing a medical emergency at Saturn cannot wait 160 minutes for a physician's response. They need to act immediately, with whatever knowledge and equipment they have. The training and equipment required for this level of medical autonomy is not currently standard for astronaut selection or spaceflight preparation. Let us now talk about what the Saturn system actually offers, why anyone would want to go there despite all these challenges. Because the scientific and exploratory case for Saturn is genuinely extraordinary. Saturn itself is one of the most physically interesting objects in the solar system. Its ring system, the most prominent and most complex in the solar system, is composed of billions of individual particles ranging from tiny ice crystals to chunks of ice and rock tens of meters across. The rings extend to approximately 282,000 kilometers from Saturn's center, nearly equal to the Earth-Moon distance, yet are typically only 10 to 100 meters thick. The ring particles are in dynamic interaction with Saturn's moons. Shepherd moons confine certain rings. Moon resonances create gaps and structures, and the rings are continuously being depleted by particle loss into Saturn's atmosphere and replenished by material from the moons. The rings are young. Measurements from the Cassini mission, which orbited Saturn from 2004 to 2017 and is the most successful planetary mission in history by many measures, determined that the rings are at most 100 to 400 million years old. The solar system is 4.5 billion years old. The rings are a recent addition, not a primordial feature of Saturn, but something that formed when the solar system was already 4 billion years old. Their origin is uncertain. The leading hypothesis involves the disruption of a large moon or the capture and tidal disruption of a passing Kuiper belt object. The ring system is also being lost. Cassini measured that ring material is continuously raining down into Saturn's atmosphere at a rate of approximately 1 to 100 kilograms per second. At this rate, the rings will be gone in 100 to 300 million years. We happen to live in the brief cosmological window when Saturn has spectacular rings. Before the rings formed, Saturn was a plain gas giant. After the rings are gone, it will be again. The current ringed Saturn is a temporary phenomenon, and we are lucky enough to exist at the specific moment when it is present. Saturn's moon system is extraordinary in its diversity. Titan, the largest moon and the second largest moon in the solar system after Ganymede, has a thick nitrogen atmosphere with a surface pressure 1.5 times Earth's. It has lakes and seas of liquid methane and ethane on its surface. It has methane rain, methane rivers, methane clouds. It has dunes made of organic compounds blown by winds. It is the only world in the solar system other than Earth with stable liquid on its surface. Titan's atmosphere is in some ways similar to Earth's early atmosphere before photosynthesis began producing oxygen. It is rich in organic compounds, nitrogen, methane, ethane, more complex hydrocarbons, created by the photochemistry of methane in the presence of nitrogen under ultraviolet radiation. These organic compounds are the same fundamental building blocks from which the chemistry of life is constructed. Titan is a natural laboratory for studying prebiotic chemistry, the chemistry that preceded life on Earth, at a scale impossible to replicate in any terrestrial laboratory. NASA's Dragonfly mission, a nuclear-powered rotorcraft lander scheduled to arrive at Titan in 2034, will conduct the first in situ study of Titan's surface chemistry. It will fly from site to site, sampling the surface materials and analyzing their composition. Dragonfly is a robotic precursor that will address many of the most urgent scientific questions about Titan, but it will not resolve the deepest questions about whether life or its precursors exist there. Those questions may ultimately require the kind of complex, adaptive investigation that only humans can provide. Enceladus, one of Saturn's smaller moons at only 500 kilometers in diameter, is one of the most scientifically exciting objects in the solar system. Cassini discovered that Enceladus has active geysers erupting from its south polar region, jets of water vapor, ice particles, organic compounds, and molecular hydrogen shooting into space from cracks in the ice surface called tiger stripes. These plumes contain the ingredients for life: liquid water, organic chemicals, an energy source from hydrothermal activity on the ocean floor. Enceladus has a global subsurface ocean of liquid water beneath its icy crust. The ocean is in contact with the rocky sea floor, and hydrothermal activity, similar to hydrothermal vents on Earth's ocean floor, provides chemical energy that could support microbial life. Earth's deep ocean hydrothermal ecosystems support thriving communities of life without any sunlight. If analogous ecosystems exist in Enceladus's ocean, the Moon could be inhabited right now. The key word is could. We do not know. Cassini flew through the plumes and detected their composition, but could not carry instruments sensitive enough to definitively detect biological molecules or life. A mission specifically designed to detect life in the Enceladus plumes, flying through repeatedly with advanced mass spectrometers capable of identifying complex biological molecules, could potentially answer the question of whether Enceladus is inhabited. This would be the most consequential scientific discovery in human history. The case for human presence in the Saturn system, as opposed to robotic exploration, rests on the specific limitations of robots in conducting complex adaptive investigations. A robotic mission to Enceladus must be planned years to decades in advance, must operate within the constraints of pre-programmed decision trees, cannot adapt in real time to unexpected discoveries, cannot exercise the kind of exploratory judgment that a trained scientist exercising curiosity brings to an investigation. A human geologist on Titan could identify scientifically interesting features that no robotic mission was programmed to look for, could exercise the pattern recognition, the intuition, the flexible hypothesis testing that is the essence of field science. But the case for human presence in the Saturn system is confronted directly by the physical realities we have been examining: the radiation, the microgravity, the years of transit, the psychological isolation, the propulsion requirements. These are not details to be worked out in mission planning. They are fundamental constraints that determine whether a mission is possible at all. Let us now examine what the Saturn approach environment is actually like, what a spacecraft and crew would encounter when they actually arrived at Saturn after years of transit. The approach to Saturn is not the approach to an empty space with a planet in the middle. It is the approach to a complex and potentially hazardous system with multiple components that interact in ways that present specific risks. The rings are not empty space with a few particles scattered through them. At the inner edges of the rings, the B ring and C ring, the particle density is high enough that a spacecraft cannot safely enter without hitting particles at high velocity. Cassini navigated carefully in the region between the innermost ring and Saturn's cloud tops, a gap of approximately 2,000 kilometers that was thought to be relatively clear of particles. Even there, Cassini's dust detector recorded impacts from particles during its final months of operation. A crewed spacecraft transiting through this gap, if such a transit were required, would need shielding capable of withstanding impacts from particles at orbital velocities. Saturn's radiation environment is less severe than Jupiter's. Jupiter has by far the most intense radiation belts in the solar system, but is still significant. Saturn has radiation belts trapped in its magnetic field, containing energetic protons and electrons that would produce elevated radiation doses for a spacecraft crew in Saturn orbit. The dose rate depends strongly on the specific orbit. Higher inclinations and smaller orbital radii produce more radiation. A mission that spent months or years in Saturn orbit would accumulate significant additional radiation dose beyond what was received during the transit. Titan presents its own approach and landing challenges. The thick atmosphere that makes Titan scientifically interesting, 1.5 times Earth's surface pressure, means that landing on Titan requires descent through the atmosphere. The Huygens probe that Cassini delivered to Titan in 2005 descended on a parachute for approximately 2.5 hours before landing. A crewed lander on Titan would need heat shielding for atmospheric entry. Titan's atmosphere is cold, approximately -179 degrees Celsius at the surface, but the entry velocities produce aerodynamic heating, followed by a parachute or powered descent. The surface of Titan poses specific challenges. The terrain includes vast dune fields of organic compounds, possible cryovolcanic features, lakes and seas of liquid methane, and river channels carved by methane flows. The surface is cold enough that any exposed metal or polymer experiences extreme brittleness. Materials that are flexible and strong at room temperature become rigid and prone to fracture at -179 degrees Celsius. Suit materials, seals, actuators, and all other components of a Titan surface system must be designed and tested at these temperatures. The chemistry of Titan's surface, rich in complex organic compounds, including potential prebiotic molecules, presents both scientific opportunity and contamination risk. Contamination is a specific concern for any mission to a potentially inhabited environment. The Committee on Space Research, COSPAR, Planetary Protection Guidelines, designate Enceladus and the subsurface ocean of Titan as Category 4 targets, requiring strict sterilization of any spacecraft that would contact or sample those environments. For a crewed mission, the contamination problem is essentially unsolvable. Human beings carry approximately 37 trillion microorganisms on and in their bodies, and maintaining complete biological isolation from a moon's environment while conducting surface operations is not achievable with any current or foreseeable suit technology. This means that a crewed mission landing on or near Enceladus's south polar region, the scientifically most interesting part of the Moon, would inevitably contaminate the environment with Earth organisms and potentially compromise the very scientific investigation the mission was intended to conduct. This planetary protection constraint does not apply to Saturn itself, or to missions that only observe Enceladus from orbit or through remote sensing. But it is a significant constraint on what a crewed Saturn mission could actually do once it arrived. Let us now talk about what a realistic crewed Saturn mission architecture might look like, what has been proposed, what has been studied, and why none of the proposals have advanced beyond concept studies. Various concept studies for human missions to the outer solar system have been conducted by NASA, by academic researchers, and by independent organizations over the decades. The most detailed studies generally focus on Mars as the first deep space human destination. Saturn is generally considered a potential second or third destination after Mars, and possibly after a human return to the Moon. The fundamental architecture problem for a Saturn mission is the conflict between the desire to minimize transit time, to reduce the physiological and psychological burden on the crew, and the propulsion capability required to achieve fast transits. A 6-year transit each way is physiologically brutal, but achievable with advanced nuclear thermal propulsion. A 1-year transit each way would be far less damaging, but requires propulsion technology, perhaps fusion propulsion or advanced nuclear electric propulsion, that does not yet exist. The minimum energy trajectory from Earth to Saturn, the most fuel-efficient path using gravity assists, requires approximately 6 years for an unmanned spacecraft, and would require comparable or longer times for a crewed spacecraft, unless additional propulsion capability is used to speed the transit at the cost of more propellant. An opposition-class mission, one that uses a higher energy trajectory to minimize total mission time, could potentially reach Saturn in approximately 2 to 3 years with advanced propulsion. But the return journey would require the same time and the same propellant. The propellant mass required for a fast, crewed round trip to Saturn with any currently available or near-term propulsion technology is so large that it would require either a massive orbital assembly operation, building the spacecraft in orbit from dozens of launches, or the development of propulsion technologies that are currently at low technology readiness levels. Neither option is near-term achievable within any realistic budget scenario. One specific architectural option that has been studied is a one-way mission, sending a crew to Saturn with no intention of return, establishing a permanent human presence in the Saturn system. This option has been seriously proposed by some researchers as the only technically feasible way to conduct meaningful human exploration of the outer solar system with near-term technology. The crew would be volunteers, accepting a permanent relocation to the Saturn system, sustained by resupply missions from Earth for the basic necessities that cannot be produced locally, and by local resource utilization to the extent possible. The ethical dimensions of such a mission are complex. Volunteers accepting a permanent one-way mission to Saturn with no possibility of return are making the decision analogous to the first settlers of a genuinely new world. People who board a ship knowing they will never see their homeland again. Throughout human history, such decisions have been made, and the resulting settlements have sometimes thrived. The analogy to colonization of remote terrestrial environments is imperfect. No terrestrial environment is as isolated as Saturn. But the fundamental human capacity to relocate permanently to harsh environments for the purpose of exploration and settlement is well established. Whether such a mission would be ethically acceptable, whether governments or private organizations would sanction the permanent exile of volunteer crew members to a location from which return is essentially impossible, is a question that goes beyond physics into philosophy and policy. Different cultures and ethical frameworks would reach different conclusions. What is clear is that the physics does not forbid permanent one-way missions to Saturn, even when it makes round-trip missions extraordinarily difficult. Let us now talk about the specific timeline of what a Saturn mission would experience on arrival, the specific scientific and operational activities that would fill the years spent in the Saturn system. Saturn's orbital period around the Sun is approximately 29.5 years. Saturn's seasons, each lasting approximately 7.4 Earth years, produce significant changes in the appearance and behavior of the atmosphere, the rings, and the moons. A crewed mission spending even a few years at Saturn would observe Saturn through a substantial fraction of one of its seasons, more than any robotic mission has observed in a single continuous campaign. The scientific program at Saturn would be built around several major themes. Saturn's atmosphere, its banded structure, its storms, its winds, its deep interior, would be studied continuously from orbit. The hexagonal polar vortex, a persistent hexagonal cloud pattern at Saturn's north pole, approximately 25,000 kilometers across, would be observed through its seasonal evolution. Probe releases into Saturn's atmosphere could measure the temperature, pressure, chemical composition, and wind speed profiles from the cloud tops to depths where pressure crushes any spacecraft. The ring system would be studied in detail. Its particle composition, size distribution, dynamics, and interactions with Saturn's moons. The structure of the rings contains information about the distribution of mass within Saturn and about the tidal forces exerted by Saturn on the ring material. The gaps and waves and spirals in the ring structure are traceable to resonances with specific moons and provide data on Saturn's internal structure that cannot be obtained by any other method. The Moon system would be the primary focus of detailed investigation. Titan would receive multiple dedicated missions, atmospheric probes, surface landers, lake samplers. Enceladus would be studied exhaustively, its plumes analyzed for molecular complexity, its ice surface mapped, its heat flow measured to characterize the hydrothermal activity driving the plumes. Other moons, Dione, Rhea, Iapetus, Hyperion, Mimas, each with their own distinctive geology and history, would be visited and characterized. The scientific return from years of intensive human-led investigation in the Saturn system would be transformative. The Cassini mission, The most successful robotic Saturn mission was a 13-year orbital campaign that produced thousands of scientific papers and reshaped our understanding of planetary science. A crewed mission with the adaptability and investigative capacity that humans provide could potentially exceed Cassini's entire scientific output in a single field season of intensive investigation. This is the scientific case for going. It is compelling. It is genuine. The Saturn system contains some of the most scientifically important objects in the solar system. Enceladus, with its potentially inhabited subsurface ocean, Titan, with its prebiotic chemistry, the Ring system, with its record of early solar system history. The physical case for returning is what makes the mission so extraordinarily difficult. Every gram of material that must be brought back from Saturn, including propellant for the return journey, must be launched from Earth or produced in the Saturn system. The energy required for the return journey is comparable to the energy required for the outbound journey. Everything that makes reaching Saturn hard also makes returning from Saturn hard. Let us talk about what fuel production in the Saturn system might look like, whether local resource utilization could solve the propulsion problem that makes return so difficult. Saturn's atmosphere is approximately 96% hydrogen and 3% helium, with trace amounts of other compounds. The hydrogen is available in essentially unlimited quantities. Saturn is the second largest reservoir of hydrogen in the solar system after Jupiter. If hydrogen could be extracted from Saturn's atmosphere and combined with oxygen to produce liquid hydrogen and liquid oxygen rocket propellant, the return propulsion problem would be substantially reduced. The challenge is extracting the hydrogen. Saturn's atmosphere is not accessible in the way that the surface of a rocky body might be. The cloud tops are at pressures of approximately 1 bar and temperatures of approximately minus 139 degrees Celsius. Below the cloud tops, the pressure and temperature increase with depth. The winds in Saturn's atmosphere are among the fastest in the solar system, reaching 1,800 kilometers per hour in the equatorial jet streams. Scooping hydrogen from Saturn's atmosphere would require a spacecraft that can tolerate these conditions while extracting, processing, and storing hydrogen in useful quantities. This is technically extremely difficult. No mission has ever extracted resources from a gas giant atmosphere, and the engineering required would be far beyond anything currently available. Even if the hydrogen extraction problem could be solved, the oxygen problem remains. Saturn's atmosphere contains essentially no oxygen. Oxygen would need to be produced by electrolysis of water ice from the moons, specifically from Enceladus or other icy moons, or carried from Earth. Titan's atmosphere and surface offer a different resource utilization possibility. Titan has abundant nitrogen. Its atmosphere is 95% nitrogen, and abundant methane and ethane in its lakes and seas. Nitrogen and methane could, in principle, be used as propellant for a nitrogen-methane rocket engine, a propulsion system similar to what SpaceX's Raptor engine uses with terrestrial methane and liquid oxygen. If methane could be extracted from Titan's lakes, and liquid oxygen could be produced from water ice on other moons, a propellant production capability could, in principle, be established in the Saturn system. This is the vision behind proposals for a sustained human presence at Saturn. Not a single mission that carries all its supplies from Earth, but a permanent establishment that progressively develops the capability to extract resources from the local environment and reduce its dependence on Earth for resupply. The first missions would carry everything they need from Earth, a massive and expensive undertaking. Subsequent missions would increasingly rely on locally produced propellant, locally grown food, locally manufactured materials. Over decades, the Saturn presence would become more self-sufficient. This vision is compelling, but it is also long horizon in a way that goes beyond normal mission planning. The first crewed mission to Saturn would not be self-sufficient. It would depend completely on Earth for resupply. Its crew would either return to Earth, if the propulsion and resources for return are available, or remain permanently in the Saturn system, sustained by an ongoing supply chain from Earth, in the expectation that future missions would eventually establish the infrastructure for local resource production. Whether such a long-term commitment to Saturn exploration could be sustained, whether the political and financial support would persist across decades and administrations and economic cycles, is the most uncertain aspect of the entire enterprise. The history of space exploration suggests caution. Programs that require sustained, multi-decade commitment without near-term tangible results have historically struggled to maintain political and financial support. Apollo lasted less than 4 years of surface operations. The International Space Station has been continuously inhabited since 2000, but has faced repeated budget pressures. A Saturn program, requiring decades of sustained investment before producing the self-sufficiency that would make it genuinely viable, would face extraordinary institutional challenges. Let us now talk about what autonomous operation would look like in the Saturn system. How a crew would manage their spacecraft and conduct their mission with minimal support from Earth. The 80-minute one-way communication delay means that ground control cannot monitor and respond to Saturn system operations in anything approaching real time. Every decision that needs to be made in less than 160 minutes, 80 minutes for the question to reach Earth and 80 minutes for the answer to return, must be made by the crew independently. In practice, almost every decision in a Saturn mission would be made by the crew because the timescales of spacecraft operations, scientific investigation, and emergency response are all far shorter than 160 minutes. This represents a fundamentally different operational paradigm from current human spaceflight. SS astronauts have continuous communication with mission control and operate in a highly monitored, highly supported environment. Every major decision is reviewed by ground teams. Every anomaly is analysed by hundreds of ground support personnel. The crew is never truly alone in the operational sense. Saturn mission crew members would be alone in the operational sense. They would need to diagnose and resolve spacecraft anomalies without ground support. They would need to conduct scientific investigations without real-time scientific guidance from Earth. They would need to make medical decisions without consulting physicians. They would need to navigate emergencies without external assistance. The only resource available would be whatever knowledge and capability they brought with them. This requires a different kind of crew, not just technically competent, technically autonomous, not just psychologically resilient, self-sufficient. The crew selection and training for a Saturn mission would need to produce individuals capable of functioning at the highest level of professional competence without external validation or support for years at a time. Whether such individuals can be identified, trained and maintained in peak condition for the duration of a multi-year Saturn mission is an open question. Artificial intelligence systems could provide substantial support. An advanced AI system with access to the complete technical documentation of the spacecraft, the complete scientific literature of Saturn system science, and the complete medical knowledge base of Earth medicine could serve as an expert consultant for the crew, not replacing human judgment, but augmenting it with rapid access to relevant information and analytical support. The development of such systems is one of the areas where near-term technology progress could meaningfully reduce the operational demands on a Saturn mission crew. But there are limits to what AI augmentation can provide. The AI is only as good as the information it was trained on and the scenarios it was tested against. Novel situations, unexpected equipment failures, unexpected scientific discoveries, unexpected interpersonal crises may require responses that go beyond any training or reference database. The ultimate resource in these situations is human creativity, adaptability, and judgment, the qualities that make human exploration genuinely different from robotic exploration. Let us talk about what communication with Earth would actually be like from Saturn. Not just the delay, but the specific experience of maintaining connection with the homeworld across that distance. A message sent from Earth today arrives at Saturn approximately 80 minutes later. A message sent from Saturn arrives at Earth 80 minutes later. A conversation, the intuitive human mode of interpersonal communication, is not possible. What is possible is the exchange of carefully composed messages, each complete in itself, each awaiting a response that will arrive at minimum 160 minutes later. This changes the character of human relationships across the distance. Family conversations are not conversations in the real-time sense. They are an exchange of monologues. A crew member cannot hear their child's voice and respond to what the child says in real time. They can send a message, wait more than 2.5 hours for a response, then send another message in response. The emotional texture of the relationship changes fundamentally. Some relationships may adapt successfully to this asynchronous mode. Letters, which are inherently asynchronous, have sustained deep human connections across great distances throughout history. The psychological research on long-distance relationships suggests that they can be maintained with appropriate communication strategies. But the specific quality of an 80-minute delay, longer than a typical conversation, shorter than a day, creates a peculiar temporal situation that has no historical analogue and whose effects on long-term human relationships are not known. The crew would also be communicating with Earth through increasingly outdated information. A crew member's family on Earth exists in a present that the crew member cannot observe in real time. News from Earth, the events that shape the world the crew members came from and will return to, arrives as dispatches from an increasingly distant past. Over years, the crew's mental model of Earth, the world they carry in memory, becomes progressively less accurate as Earth changes in ways they can only partially observe through the time-delayed information they receive. This temporal displacement, living in Saturn time while knowing that Earth time is passing differently, and producing events you can only observe with an 80-minute delay, is a specific form of psychological isolation that has no direct analogue in any previous human experience. Its effects on crew psychology would need to be carefully monitored and managed throughout the mission. The crew would also be communicating in an information environment that progressively differs from Earth's. The scientific discoveries made in the Saturn system, the new understanding of Titan's chemistry, the findings about Enceladus's ocean, the ring system dynamics, would be known to the crew before Earth because the crew is observing them directly, while Earth can only receive transmitted reports. The crew would experience events, emergencies, discoveries, interpersonal crises that Earth would not learn about for 80 minutes. They would live in an informational frontier, always ahead of Earth's knowledge of their own situation. This is one of the specific characteristics of deep space exploration that distinguishes it most sharply from all previous human experience. The crew is not just physically distant from Earth, they are informationally ahead of Earth. They know things that Earth does not yet know. They experience events that Earth will not know about for hours. They exist in a relationship with Earth that is fundamentally asymmetric, not just in distance, but in information. The Saturn mission crew would be the most informationally autonomous human beings in history. Cut off from the Earth-centered information environment in which all previous human beings have lived, operating with a body of knowledge about their environment that Earth is always 80 minutes behind, making decisions based on information that will not reach Earth until the decisions have already been made and their consequences are underway. This is what going to Saturn actually means. Not just travelling far, being far, informationally, temporally, physiologically, psychologically, being the most distant human beings from their origin that any human beings have ever been, being beyond reach in every practical sense, being alone in the most complete way the solar system allows while still within it, and looking at rings, and listening to the data, and knowing that Enceladus might be inhabited, and knowing that Titan's chemistry is telling a story about the origin of life, and being the only human beings close enough to read that story directly. That is why anyone might go to Saturn knowing they may never come back. Not because they did not understand the physics, because they understood it completely and went anyway. Let us talk about what the Saturn system looks like up close, what a crew would actually see and experience when they finally arrived after years of transit, because this experience is one of the least discussed and most extraordinary aspects of a Saturn mission. During the years of outbound transit, Saturn would be changing in the spacecraft's view. For the first year or two, it would appear as a bright star, distinguishable from other stars by its steady, non-twinkling light and its slight yellowish colour, but not yet showing any disk to the naked eye. As the spacecraft approached, closing the distance from 1.4 billion kilometres to hundreds of millions to tens of millions, Saturn would begin to resolve into a disk, then into a disk with rings, then into a visibly ringed planet with visible bands in the atmosphere and visible moons. The transition from star to planet to ringed world to the most visually spectacular object in the solar system would happen over weeks as the spacecraft decelerated into Saturn orbit. The psychological effect of this transition on a crew that had been looking at an unchanging star for years would be profound. Saturn growing from a point to a world, visibly growing day by day, the ring system becoming clearer, the moons becoming resolvable as distinct objects rather than points of light, would be one of the most extraordinary visual experiences available to human beings. At closest approach, in orbit around Saturn, the view would be incomparable to anything available from Earth or from any Earth orbital perspective. Saturn would fill a substantial portion of the sky. The ring system, seen from within the Saturn system at close range, would appear not as the thin ellipse visible from Earth through a telescope, but as a vast, flat plane of material extending across the sky in both directions, the individual ring particles not resolvable, but the structure of the rings, the Cassini division, the A ring, the B ring, the C ring, the narrow F ring, distinct and dramatic. The play of sunlight on the rings from different angles would produce extraordinary visual effects. Sunlight passing through the rings from behind, the rings backlit by the sun, produces a different appearance than sunlight reflected off the rings. The shadows of the rings on Saturn's cloud tops shift with the season and the geometry of observation. The shadows of Saturn on the rings, when the spacecraft is positioned such that Saturn blocks the Sun from illuminating part of the ring plane, reveal the three-dimensional structure of ring particle concentrations. Saturn's cloud tops at close range would show the banded structure in detail, the equatorial jet stream flowing at 1,800 kilometers per hour, the complex boundary regions between atmospheric bands where storms and vortices develop, the enormous oval storms that persist for months or years, the hexagonal polar vortex, invisible from Earth as a geometric feature first imaged by Cassini, would be visible in the northern sky of Saturn. The moons would be distinct worlds. Titan, larger than the planet Mercury, would show a featureless orange disk to the naked eye because its thick atmosphere scatters and absorbs the sunlight before it can illuminate the surface. But through instruments, it would reveal the lake districts, the dune fields, the river channels, the potential cryovolcanic features that Cassini imaged through its radar and near-infrared cameras. Titan's atmosphere would be visually spectacular. The orange haze layers visible at the limb, the methane clouds developing over the polar regions as the season advances. Enceladus would be visibly active. The plumes erupting from the south polar tiger stripes, water vapor and ice particles shooting 500 kilometers into space would be visible from orbit as bright streaks against the dark sky when Enceladus is positioned between the spacecraft and the Sun. Watching Enceladus's plumes in person, knowing that those plumes contain material from a potentially inhabited ocean beneath the ice, would be one of the most scientifically and emotionally intense experiences available in the solar system. The smaller moons, Dione, Rhea, Iapetus, Mimas, each have their own visual identity. Iapetus has its famous two-tone appearance, one hemisphere almost as dark as coal, the other almost as bright as fresh snow, which gives it an appearance unlike any other moon. Mimas, with its enormous Herschel crater making it resemble the Death Star, would be striking at close range. Hyperion, the irregularly shaped chaotic tumbler with its sponge-like surface texture, would look like no other object in the solar system. The view from inside the ring plane, below the rings looking up at them from below, would be available to a spacecraft in an inclined Saturn orbit. From this perspective, the rings would appear as an enormous flat plane overhead, semi-transparent, with sunlight filtering through the particles and producing diffuse lighting, unlike anything available anywhere else in the solar system. This view is unique to observers in the Saturn system. It cannot be reproduced from any other perspective. During the equinox, when the Sun is in the plane of the rings and illuminates the rings edge on, the ring structure would cast dramatic shadows across Saturn's cloud tops, and the rings themselves would appear as an impossibly thin line of light. The Cassini mission observed Saturn's equinox in August 2009 and produced some of the most spectacular images in the mission's history. A crew present at equinox would have the direct experience of this extraordinary geometric alignment. The darkness at Saturn, the sky background, would be noticeably different from the sky as seen from Earth or from Earth orbit. Saturn is 9.5 astronomical units from the Sun. Sunlight at Saturn is approximately 1/90th the intensity of sunlight at Earth. The Sun would appear significantly smaller than it appears from Earth, approximately 1/3 the angular diameter, and significantly dimmer. Solar panels, which work well in the inner solar system, are far less effective at Saturn, which is why Cassini used nuclear power, RTGs, rather than solar panels. A crewed spacecraft at Saturn would similarly rely on nuclear power. The stars would be the same as seen from Earth. The distances to even nearby stars are so much larger than the Saturn-Earth distance that the stellar parallax shift is undetectable to the naked eye. But in the dark sky of Saturn orbit, with the Sun reduced to a bright but small disk and no atmospheric scattering, the stars would blaze with the clarity of deep space. The Milky Way would be spectacular. The planet Earth, visible from Saturn as a bright blue dot near the Sun, would be a tiny point of light carrying all of human civilization and all of human history in a single pixel. This view, Earth as a pale blue dot seen from the vicinity of Saturn, is one of the most profound available in the solar system. Carl Sagan wrote of the Voyager 1 image of Earth taken from 6 billion kilometers, just beyond Saturn's distance, as the most powerful argument for the importance of taking care of each other and the only home we have ever known. A human being seeing Earth as a blue dot from Saturn orbit would have an experience that no photograph and no description can fully convey. The direct perception of home as a small, vulnerable, impossibly distant point of light. Let us now talk about the specific question of children at Saturn, not as a fanciful speculation, but as a serious consideration for any permanent or long-term human presence in the Saturn system. If a crew is to remain permanently at Saturn, if the mission is intended to establish a long-term human presence rather than a temporary visit, the question of reproduction becomes relevant within years of arrival. Human beings reproduce. A community of human beings confined to a spacecraft or habitat for decades will eventually produce children, either by design or by circumstance. Children born in the Saturn system would face all the physiological challenges of spaceborne children discussed in other contexts: reduced gravity developmental effects, radiation exposure throughout development, the specific medical challenges of childhood without the resources of Earth medical infrastructure. These challenges are severe and largely unstudied. But there is a deeper consideration. A child born in the Saturn system has not chosen to be there. They cannot consent to the conditions of their existence, the radiation, the isolation, the physiological challenges, the distance from Earth. Their parents made the choice to go to Saturn. They made no choice at all. Whether it is ethical to bring children into existence in conditions as extreme as a Saturn mission is a question that goes to the foundations of reproductive ethics and parental responsibility. The same question has been asked in different forms about children born into other difficult circumstances: extreme poverty, war, remote communities with limited resources. The answers society has reached are complex and contested. The Saturn case is an extreme version of these questions, more extreme than any terrestrial analogue, and the ethical framework for addressing it does not currently exist in developed form. From a purely practical standpoint, a growing community of Saturn system humans would require educational systems, medical systems, social systems, and governance systems appropriate to its size and needs. The first generation raised in the Saturn system, without any direct experience of Earth, would have a fundamentally different relationship to humanity's home planet than their parents. Earth would be an abstract concept for them, a place they know from records and communications, but have never experienced. Their world would be the Saturn system. Their home would be whatever habitat they were raised in. Their sense of normal would be calibrated to conditions that every Earth human would consider extreme. This is potentially the most profound implication of permanent human presence in the Saturn system. Not the scientific discoveries, or the propulsion challenges, or the physiological risks, but the creation of a population of human beings for whom Saturn is home, and Earth is a distant legend. The beginning of genuine human divergence into communities adapted to different worlds. Let us now talk about what robotic precursors to a crewed Saturn mission would look like. What missions would need to succeed before the human mission could be seriously planned. The current state of Saturn exploration is robust in robotic terms. Cassini's 13-year mission from 2004 to 2017 provided comprehensive orbital coverage of Saturn and its system. The Huygens probe provided a surface view of Titan. Dragonfly will conduct aerial exploration of Titan's surface beginning in 2034. But several critical gaps in knowledge would need to be addressed before a crewed mission could be designed with acceptable risk. The first gap is the radiation environment in Saturn orbit in detail sufficient for crew safety planning. Cassini measured the radiation environment, but not with instruments optimized for crew dosimetry. A dedicated radiation survey mission, characterizing the particle radiation belts, their variability with solar activity, and their distribution through the Saturn system, would be essential for crew safety planning. The second gap is the resource availability in the Saturn system. Any mission that hopes to produce propellant or other critical resources locally needs to know in detail what resources are available, where, and in what form. A dedicated resource survey mission, characterizing the composition and accessibility of ice on the moons, the extractability of hydrogen from Saturn's atmosphere, the availability of other materials, would be needed. The third gap is the detailed characterization of Enceladus's ocean. The most compelling scientific target for a crewed mission is Enceladus, specifically the question of whether its subsurface ocean is inhabited. A dedicated Enceladus mission, perhaps a life detection orbiter that flies repeatedly through the plumes with instruments far more capable than Cassini's, would either confirm or refute the presence of biological molecules in the plumes and guide the design of any crewed investigation. The fourth gap is the engineering demonstration of long-duration life support systems at Saturn distance, where the communication delay makes Earth-supported fault diagnosis and repair impossible. An extended robotic precursor, perhaps a deep space habitat placed in Saturn orbit and operated for years by tele-robots to demonstrate the reliability of life support systems in this environment, would significantly reduce the engineering risk for a crewed mission. All of these precursor missions would take decades to plan, launch, travel, and produce results. The travel time to Saturn alone is 6 to 7 years for a fast trajectory. A robotic precursor launched today would not produce results until the 2030s at the earliest. A crewed mission based on those results would not be launched until the 2040s or 2050s at the earliest under any optimistic scenario. This timeline is sobering. The people who will fly the first human Saturn mission are almost certainly alive today, but they are probably children or young adults. The mission they will fly is decades away. The decisions being made today about what robotic missions to fund, what propulsion technology to develop, what life support systems to test, these decisions will determine the shape of the crewed Saturn mission that occurs 30 or 40 years from now. This is the specific character of the Outer Solar System Exploration Challenge. It is not a challenge that unfolds on election cycle timescales or corporate quarter timescales or even decade timescales. It unfolds on generational timescales. The people who will benefit from the decisions being made today are not yet in decision-making positions. The decisions being made today will be executed by people who are not yet in their careers. This long timescale is both the challenge and the argument for starting now. Every year of delay in developing the required propulsion technology, the required life support systems, the required radiation countermeasures, the required autonomous operational protocols, every year of delay is a year added to the already long wait. The people who will fly to Saturn cannot fly there any sooner than the technology required for the mission is ready. And that technology requires decades of development, starting from today. Let us talk about the specific question of what makes Saturn worth all of this, why the specific destination of Saturn justifies the extraordinary difficulty and risk. The answer is Enceladus. Not Saturn itself, beautiful as it is. Not Titan, fascinating as its prebiotic chemistry is. Enceladus, a small moon 500 kilometers in diameter, shooting water from its interior into space, is potentially the most important destination in the solar system for addressing the question of whether life exists beyond Earth. If life exists in Enceladus's ocean, if the hydrothermal ecosystems in that dark, salty seafloor harbour organisms analogous to Earth's deep-sea vent communities, then life is not unique to Earth. Life is a phenomenon that arises wherever the conditions allow, and the conditions allow in at least 2 places in our solar system. The implication for the abundance of life in the universe would be profound. A single origin of life could be an accident of chemistry. 2 origins in one solar system would be strong evidence that life is a natural consequence of chemistry wherever liquid water, organic compounds, and energy sources co-occur. And those 3 ingredients, liquid water, organic compounds, energy, exist throughout the universe. In the subsurface oceans of icy moons around other giant planets in other solar systems, in the wet interiors of large asteroids and dwarf planets, in the habitable zones of the 100 billion galaxies containing hundreds of billions of stars. If life exists in Enceladus's ocean, the universe is almost certainly full of life. The discovery of a second origin of life in our own solar system would be the most significant scientific discovery in human history, exceeding the Copernican revolution, exceeding the discovery of evolution, exceeding every other revision in our understanding of our place in the cosmos. This is what is potentially waiting in the Saturn system. Not certain, not confirmed, but possible, plausible, suggested by the specific chemistry of the Enceladus plumes, the detection of hydrogen suggesting active hydrothermal chemistry, the presence of complex organic molecules, the liquid water, the apparent long-term stability of the ocean over geological time. A crewed mission to the Saturn system with the specific goal of definitively answering the question of life in Enceladus's ocean would be the most consequential scientific mission ever undertaken. Not because the crew would necessarily find life, because they would be positioned to conduct the investigation that could definitively answer the question, and because that question is the most important question in science. The difficulty of the mission, the radiation, the years of transit, the physiological cost, the propulsion challenge, the psychological isolation, the risk of no return, all of this is the price of addressing the most important question we can ask: whether we are alone, whether life is a cosmic phenomenon or an earthly accident, whether the universe is inhabited or empty. Saturn is the gateway to that answer. Enceladus holds it.
And the difficulty of reaching Enceladus is the measure of how important the answer must be to justify the attempt. Let us talk about what legacy a Saturn mission would leave, not just the scientific discoveries, but the human legacy, the meaning that the mission would carry for the people who flew it and for the civilization that sent them.
Every great exploratory mission leaves multiple legacies. The scientific legacy, the data, the discoveries, the questions answered and new ones opened. The technological legacy, the propulsion systems developed, the life support systems proven, the navigation techniques demonstrated that make subsequent missions possible. The cultural legacy, the photographs, the stories, the expansion of human imagination that comes from knowing that a human being stood there and looked back. The Apollo program left all three legacies. Its scientific legacy was the lunar sample collection and the geophysical characterization of the Moon that is still being analysed. Its technological legacy was the development of systems, computers, propulsion, life support, communications that transformed multiple industries. Its cultural legacy was the photographs, Earthrise, the blue marble, the boot print in the lunar dust, that shifted human self-perception in ways that are still reverberating. A Saturn mission would leave comparably profound legacies. The scientific legacy of definitively addressing the question of life in Enceladus's ocean, whatever the answer, would be transformative. The technological legacy of developing the propulsion and life support systems for deep space human missions would enable subsequent missions to the outer solar system and eventually beyond. The cultural legacy of the first humans in the outer solar system, the photographs of Saturn from human eyes rather than robotic cameras, the stories of years in deep space, the lived experience of the most distant human journey, would expand human self-conception in ways comparable to Apollo. But the Saturn legacy would also include something Apollo did not: the legacy of a community that chose to go knowing they might not return. The legacy of people who weighed the physics honestly and accepted its implications and went anyway. The legacy of a civilization that reached beyond the comfortable and the safe and the readily achievable into something that required everything they had and perhaps more. This kind of legacy is the one that changes what people believe is possible, not just for space exploration, but for human ambition generally. The message of Apollo was that impossible things are achievable if you commit resources and ingenuity and courage. The message of a Saturn mission would be something more severe, that some things are achievable only at the cost of everything, and that some questions are worth that cost. Whether our civilization is currently capable of believing that, capable of sustaining the commitment and accepting the cost, is uncertain. The history of human exploration suggests that the capacity exists. Whether it will be exercised for Saturn specifically, at the specific time when the technology becomes available, with the specific political and social will required, that is what cannot be predicted from the physics alone. The physics says Saturn is reachable. The physics says return is extremely difficult. The physics says Enceladus may be inhabited. The physics says the only way to know for certain requires going there. Everything else, the will, the funding, the decision, the commitment, is human. And human things are the hardest things to predict. Let us talk about what the specific experience of the transit would be like at the human level, not the engineering parameters or the medical statistics, but the lived texture of spending 3 to 6 years travelling through interplanetary space towards Saturn. The first months would likely be characterized by a heightened sense of purpose and novelty. The crew just left Earth, the most significant departure of their lives, perhaps of any human lives, and they are engaged with the systems of the spacecraft, establishing routines, conducting initial scientific observations, experiencing the specific novelty of deep space for the first time. Earth is receding. Saturn is a bright star ahead. The solar system is opening up around them in ways that no earthbound perspective allows. Mars missions researchers use the term salutogenesis, the process of health generation, of actively building wellness rather than merely preventing illness, to describe the psychological approach required for long-duration missions. The crew would need to actively construct meaning, routine, social connection and purpose throughout the years of transit. Passive endurance of the duration is not sufficient. The psychological work of maintaining mental health under these conditions is itself a demanding and continuous activity. Exercise would be 2 hours per day, mandatory, medically required. This is not optional recreation, but physiological necessity, the primary countermeasure against the bone and muscle loss that otherwise proceeds inevitably. 2 hours of exercise per day is approximately 14% of waking hours, a substantial fraction of every day, every week, every month, for years. The exercise equipment must be maintained. The exercise protocols must be varied to prevent monotony while maintaining effectiveness. The medical monitoring of exercise outcomes must be continued and the protocols adjusted as individual crew members' physiological responses are tracked. Food, one of the most significant quality of life factors on long-duration missions, would be limited to what was carried from Earth or grown on board. Current space nutrition research focuses on shelf-stable foods with adequate nutritional profiles that can be stored for years without degradation. Flavors and textures that are appealing at the beginning of a mission often become aversive after months of repetition. Food monotony is a consistent complaint in analog environment research. For years-long missions, the food system would need to be far more diverse and more flexible than anything currently used in human spaceflight. Plant growth systems capable of producing fresh food in microgravity have been studied and partially demonstrated on the ISS. A Saturn mission food system might incorporate hydroponic growing chambers, producing fresh vegetables, herbs, and possibly fruits that supplement the stored rations. Fresh food has both nutritional and psychological value. The smell, texture, and flavor of fresh produce is qualitatively different from processed, shelf-stable food, in ways that become increasingly important over extended confinement. Sleep is another critical factor. In microgravity, without the natural day-night cycle produced by the Earth's rotation, the body's circadian rhythm loses its entrainment to environmental cues. The spacecraft would need to maintain an artificial day-night cycle, lighting systems that dim and brighten on a 24-hour schedule, scheduled quiet times, and careful management of activities that disrupt sleep. Chronic sleep deprivation, which is common in space environments, produces cognitive degradation, emotional dysregulation, impaired immune function, and reduced physical performance. Over years, the cumulative effect of poor sleep quality could be severely debilitating. Privacy, or its absence, is one of the most consistently identified stressors in confined, long-duration environments. In a spacecraft small enough to be launched from Earth and operated for years without resupply, the living volume available per crew member is severely limited. The ISS has a habitable volume of approximately 388 cubic meters, shared among typically 6 crew members, approximately 65 cubic meters per person. A Saturn mission spacecraft would likely have comparable or smaller volume per person. Living in extremely close physical proximity to the same small group of people for years, with no ability to be truly alone, no ability to escape the sounds and smells and presence of the other crew members, is a profound and continuous stressor. Research on Antarctic winter over crews, who share similarly confined quarters for up to 14 months, identifies the lack of privacy and the forced proximity as among the most significant sources of interpersonal friction. Crew members who are highly compatible at the start of an isolation period become less compatible over time, simply through continuous, unavoidable exposure. Small irritants that would be insignificant in normal social life become enormously magnified by the inability to escape them. Designing for adequate privacy in a deep space habitat is a genuine engineering challenge. Individual sleeping quarters that provide visual and acoustic separation so that a crew member can withdraw from the group for personal time are considered essential by mission designers. But every cubic meter of private space is a cubic meter that costs mass to launch and maintain, competing with propellant, food, scientific equipment and life support systems for the finite mass budget of the spacecraft. The specific social dynamics of a 4 to 6 person crew over years of confinement are difficult to predict in advance. Initial crew composition seems important. Crews that are socially compatible and interpersonally skilled before departure maintain better cohesion through extended missions. But even the most carefully selected and trained crews experience the progressive social friction of forced proximity. Conflict resolution skills. The ability to identify, address, and resolve interpersonal conflicts constructively, rather than allowing them to escalate, are among the most critical crew competencies for long-duration missions. The crew would also be experiencing unique events, things that have never happened to any human being before throughout the transit. The first clear view of Saturn as a disk. The first time Saturn's rings become individually visible. The passage through the asteroid belt, visually uneventful because the asteroid belt is not the dense field of rocks depicted in science fiction, but rather vast empty space with occasional asteroid encounters, but psychologically significant as the crossing of a threshold between the inner and outer solar system. The crossing of Jupiter's orbit, entering the realm of the gas giants, definitively leaving the terrestrial planet zone behind. These threshold experiences would punctuate the transit and provide specific moments of shared significance for the crew, touchstones in the long, featureless duration of travel, events to anticipate and commemorate. The specific human experience of being the first people to cross Jupiter's orbit in a crewed spacecraft, or to see Saturn resolve into rings from a distance of 100 million kilometers, or to have Earth shrink to the point where it becomes indistinguishable from the other stars. These are experiences with no historical analogue and no adequate preparation. The crew would be keeping records, not just the official mission documentation, the engineering telemetry, the scientific data, the medical measurements, but personal records, journals, photographs, audio recordings, artworks. Human beings in extreme circumstances have always kept records of their experience. The journals of Antarctic explorers, the letters of soldiers, the diaries of prisoners, the accounts of sailors on long voyages. The crew of a Saturn mission would be producing a historical document of incalculable value, the direct first-person record of the most extraordinary journey in human history. What would they write? What would they photograph? What would they make of the years of transit, the approach to Saturn, the first views of Titan and Enceladus, the specific experience of being the most distant human beings from Earth that any human being had ever been? These are questions that cannot be answered in advance. They depend on who the crew members are, what they bring to the experience, how they are changed by it. What we can say is that the record they would produce, the specific human witness to the Saturn system, would be different in kind from anything a robotic mission could provide. Not more accurate than the measurements of robotic instruments, not more comprehensive than the data returns of a well-designed robotic mission, but different in the specific way that human witness is always different from instrument data. Subjective, contextual, emotional, embodied, carrying the specific quality of consciousness encountering reality directly. The photographs of Earth from Apollo, taken by human beings with human hands and human eyes selecting the frame, carry a quality that robotic images from the same distance do not. Not because they are more technically accurate, because they were chosen, because a human being looked through a viewfinder and decided that this particular arrangement of blue marble and black space was worth preserving. That choice, that act of human aesthetic and emotional judgment, is present in the image in a way that cannot be replicated by a robotic camera executing a pre-programmed imaging sequence. The same would be true of a Saturn mission's photographic record. The crew would photograph Saturn and its moons not just according to the scientific imaging plan, but according to what struck them as beautiful, significant, worth preserving. The specific photographs they chose to take would carry the quality of human witness, the mark of consciousness encountering one of the most extraordinary sights in the solar system, and deciding what was worth remembering. Let us now talk about the specific question of what happens if something goes wrong, if a crew member dies during the Saturn mission, or if critical systems fail, or if the mission encounters a scenario that was not anticipated in planning. These contingencies are not remote possibilities that can be dismissed as edge cases. On a multi-year deep space mission, with no possibility of rescue and no possibility of rapid return, the probability that something unexpected and serious will occur is not small. Extended operation of complex systems in harsh environments produces failures. Human beings in extreme conditions experience health crises. Interpersonal situations develop in directions that were not anticipated. The unexpected is not a possibility to be minimized, it is a certainty to be planned for. A crew member death is the most severe contingency. In Earth-based operations, the death of a team member is managed by a response system: emergency services, medical personnel, psychological support, organizational procedures for notification and recovery. On a Saturn mission, a crew member death would be managed by the surviving crew with whatever resources they had on board and whatever support Earth could provide through communications delayed by 80 minutes. The body, if not ejected into space, which raises its own ethical and practical issues, would need to be preserved or disposed of. The crew would experience grief and trauma in an environment with no support system beyond each other and whatever psychological resources they had developed. The mission would need to continue. The spacecraft still needs to be operated, the scientific work still needs to be done, the return journey, if one is planned, still needs to be executed, with one fewer crew member and with the surviving crew members grieving, traumatized, and reduced in number. The mission planners would have anticipated this. There would be procedures for crew member death, for body disposal or preservation, for redistribution of the deceased crew member's duties among the survivors, for psychological support protocols in the absence of Earth-based support. But no procedure can fully prepare a small, isolated group for the experience of losing one of their members in conditions of extreme isolation. Critical system failures present a different kind of challenge. The life support systems, the air supply, the water recycling, the thermal management, the pressure regulation, must function continuously without interruption. A failure in any of these systems that cannot be repaired would be immediately life-threatening. The spacecraft would carry spare parts for anticipated failure modes, and the crew would be trained extensively in repair procedures. But the Saturn mission would last for years, and every component of the spacecraft would experience cumulative wear and aging that could produce failure modes not anticipated during design and testing. The 80-minute communication delay means that Earth cannot provide real-time diagnostic support during a system failure. The crew would need to diagnose and repair failures in real time using whatever technical resources they had: the spacecraft's documentation, their training, their problem-solving skills, and any AI diagnostic tools available. The capacity for autonomous repair of complex system failures without ground support, using only onboard resources, is one of the most critical capabilities for a Saturn mission crew. The history of robotic space missions provides sobering data on unexpected failures. Every major robotic mission has encountered anomalies that were not anticipated in design. Cassini's mission included multiple system anomalies that required creative solutions by ground engineers, solutions that were possible only because Cassini's communication delay was manageable and ground teams had time to analyze problems and develop solutions. For a crewed Saturn mission, the timescale of required response is too short for Earth involvement in most emergencies. Navigation is another area of potential failure. The trajectory from Earth to Saturn and back is extremely precise. Small errors in trajectory execution accumulate over years of transit and can result in missing Saturn entirely or arriving at Saturn with insufficient propellant for orbit insertion. The navigation systems, the star trackers, the inertial measurement units, the radio communication with Earth for position determination, must function accurately for years. Failures in navigation systems require the crew to implement backup navigation procedures: celestial navigation using stellar references, trajectory reconstruction from available data, that must be trained and practiced, but may never have been used in a real deep space emergency before. The crew would also face the psychological challenge of making decisions under uncertainty with irreversible consequences. In a Saturn mission, many decisions about trajectory, about system operation, about medical interventions cannot be reversed once made. The propellant burned for a trajectory correction cannot be recovered. The medical treatment administered cannot be untreated. The crew would need to make these irreversible decisions based on incomplete information, under stress, without the ability to consult with Earth in real time. This decision-making environment is qualitatively different from anything experienced in previous human spaceflight. ISS crews make operational decisions, but always with ground support available, and with the option of evacuation if a decision goes badly wrong. Saturn mission crew members would make decisions knowing that the consequences, whatever they are, must be lived with in the Saturn system, with Earth 80 light minutes away, and with no possibility of rescue. Let us now talk about what a successful mission would feel like at the end. The specific experience of leaving Saturn after years in the system and beginning the long return journey to Earth. The departure from Saturn would be one of the most emotionally complex moments of the mission. The crew would be leaving a place they had lived in for years, a place that had become familiar, that they understood in ways no previous human beings had understood it, that they had studied and explored and experienced in the full depth of human perception. Leaving Saturn would mean leaving behind the specific visual experience of the ring system in the sky, the specific knowledge of Titan's methane weather, the specific understanding of Enceladus's plume chemistry gained from years of observation. If the mission had found evidence of life in Enceladus's ocean, if the crew was departing with the knowledge that the subsurface ocean beneath the South Polar Tiger Stripes was inhabited, the emotional weight of departure would be extraordinary. They would be leaving behind a living world, the only inhabited world beyond Earth ever confirmed by human observation, knowing that years would pass before any human being would return. If the mission had found no evidence of life, if the careful investigation had concluded with a negative result, or, more likely, with an ambiguous result that suggested life was possible but not confirmed, the departure would carry a different weight. The unresolved question following them back across the solar system. The knowledge that they had gotten as close as any human beings had ever gotten to answering the most important question in science, and had come away uncertain. The return transit, another 3 to 6 years of interplanetary travel, would be psychologically different from the outbound transit in some ways. The destination is now Earth, home, known, inhabited by the people they left behind years ago. But home has changed. The family members they left are years older. The friends have lived years of life that the crew did not share. The culture, the politics, the world, everything has continued without them, has changed in ways they know only through the time-delayed messages that crossed the void. The crew would be returning to a world they have not experienced in years. They have been in the Saturn system, a radically different environment, a different sky, different challenges, different rhythms of life. They have changed. Earth has changed. The specific process of re-entering Earth civilization after years of profound isolation and unique experience would be one of the most complex psychological transitions imaginable. The physiological challenges of return would be severe. After years in microgravity, even with artificial gravity in the habitat, the crew's bones, muscles, and cardiovascular systems would be significantly deconditioned compared to their pre-departure state. Re-entering Earth's gravity field would be an ordeal. The physical rehabilitation after return, rebuilding bone density, muscle mass, cardiovascular fitness, would take months to years. The vision impairment from SONS, the spaceflight-associated neuro-ocular syndrome, might be permanent in some crew members. The radiation dose accumulated over years of deep space transit might manifest as elevated cancer risk in subsequent decades. The cumulative physiological cost of the Saturn mission would not be fully apparent until years after return. But the crew would be home. If they made it home, if the propulsion worked, if the trajectory was correct, if the systems held together through years of operation, if the crew maintained the cohesion and capability to execute the return, they would be home. They would have done something that no human being had done before. They would have gone to Saturn and come back. And what they brought back, beyond themselves, beyond the scientific data, would be witness. The specific human experience of the Saturn system, the direct perception of the ring plane and the hexagonal vortex and Enceladus's plumes, the knowledge of what it is like to be the most distant human beings from Earth, the specific stories of years in deep space, what they encountered, what they felt, what they learned about themselves and each other and the universe. This witness is not quantifiable. It is not instrumentable. No sensor can capture it. No data product can represent it. It is the specific experience of human consciousness engaging with one of the most extraordinary environments in the solar system, and carrying that experience back to the civilization that sent them. That is what the return would give back to Earth. Not just data, not just samples, not just proof that the mission was survivable, but the lived experience of the Saturn system, carried in the minds and bodies of the people who were there. The most direct and irreplaceable form of knowledge that exists. Every person who went to Saturn would know things about Saturn that no one who stayed on Earth could know. Not from photographs, not from scientific papers, not from mission reports. They would know what it is like to see Saturn's rings in the sky every day for years. To watch Enceladus's plumes erupt in the black space below the craft. To experience the specific quality of sunlight at 9.5 astronomical units. Dim, steady, without the atmospheric scattering that colours Earth's sky. To be the farthest human being from home, and to feel that distance in whatever way human beings feel distances that exceed all previous experience. This knowledge, carried in the specific nervous systems of specific human beings who went to Saturn and returned, is what justifies everything. The cost, the risk, the years, the physiological damage, the possible non-return. The human experience of a new world, the irreplaceable witness of consciousness encountering the universe at its most strange and most beautiful. The rings, the plumes, the pale blue dot of Earth in the sky above Saturn's cloud tops, the years, the distance, the possible life in the ocean beneath the ice. This is why anyone might go to Saturn knowing they might not come back. Not ignorance of the physics, perfect understanding of the physics, and the decision that what waits at Saturn is worth the physics. There is a specific thought experiment that clarifies what a Saturn mission actually means. Imagine you are offered a seat on the first human mission to Saturn. The mission will take approximately 12 years from departure to return, if return is possible. During that time, you will experience radiation exposure exceeding NASA's career limits. You will experience years of microgravity producing bone and muscle loss that will require years of rehabilitation to recover from, if full recovery is possible. You will be separated from everyone you know and love by a distance that light takes 80 minutes to cross. You will make decisions that cannot be reversed without any ability to consult with Earth in real time. You may encounter situations that planning did not anticipate, that your training did not prepare you for, that your crew cannot resolve with the resources available. And you may not come back. The return propulsion may not be sufficient. A system failure may not be repairable. The physiological cost may exceed what the human body can sustain. The crew may not maintain the cohesion required to execute the return journey safely. Any of these, or combinations of them, could mean that the journey is one way. In exchange, you will see Saturn, in person, from orbit, with your own eyes, not through a spacecraft camera, not through a telescope, not in a simulation or a photograph. Saturn's rings stretching across the sky from horizon to horizon, impossibly thin and impossibly detailed. Billions of particles orbiting in perfect geometric precision around a gas giant larger than 1,000 Earths. You will see Titan's orange haze glowing against the black sky. You will watch Enceladus's plumes erupting into space, water from an ocean beneath the ice, an ocean that may be inhabited right now, that may contain living organisms that evolved independently of Earth life. You will be the most distant human beings from Earth that any human beings have ever been. You will know things about the Saturn system that no one who stays on Earth can know. Not just data, knowledge. The specific, embodied, irreplaceable knowledge of having been there. Would you go? This is not a rhetorical question designed to produce a specific answer. It is the question that defines what Saturn exploration actually means as a human enterprise. The answer depends on who you are, what you value, what you are willing to risk and sacrifice. Different people will give different answers, and all the answers are legitimate responses to a genuine dilemma. Some people will say no, rationally, clearly, with full understanding of what is at stake. No. The risk is too high. The physiological cost is too great. The separation from family and home and the familiar world is too painful. The probability of non-return is too real. Life on Earth is too valuable to trade for even the most extraordinary journey in human history. This is not cowardice. It is a fully defensible assessment of the trade-offs and a legitimate response to what the mission requires. Some people will say yes, equally rationally, equally clearly, with equally full understanding. Yes. Because the question of whether Enceladus is inhabited is more important than any consideration of personal risk. Because the human experience of the Saturn system is worth the physiological cost. Because the specific opportunity to witness something no human being has ever witnessed, to see those rings, to watch those plumes, to be the most distant human beings from home, is worth whatever it costs. Because the physics says someone has to go first, and they are willing to be that person. The difference between these answers is not a difference in intelligence or rationality or courage. It is a difference in values, in what a human life is for, in what risks are acceptable in pursuit of what goals, in what kind of knowledge is worth what kind of sacrifice. The history of exploration is full of both kinds of people, the ones who went, who accepted the costs and the risks and the possible non-return, and the ones who stayed, who built the ships and designed the missions and analyzed the data and made the going possible. Both are essential. The mission cannot happen without people willing to fly it. The mission cannot happen without the larger civilization willing to build it and sustain it and receive whatever it brings back. What we can say with confidence about Saturn is this. The physics says it is reachable. The physics says return is extremely difficult with current technology. The physics says the Saturn system contains Enceladus, a moon with a potentially inhabited subsurface ocean, shooting its internal chemistry into space where we can sample it directly. And Titan, a world with prebiotic chemistry operating at planetary scale, a natural laboratory for the chemistry that preceded life on Earth. The physics says that definitively answering the question of life in Enceladus's ocean may require human presence in the Saturn system. The physics does not say whether going is worth it. That is not a question physics can answer. Physics describes the costs, it does not evaluate them. Physics describes what is at Saturn. It does not judge whether what is at Saturn justifies the cost of reaching it. These are human questions, questions of value and priority and courage, and the specific allocation of limited human life and limited human resources toward specific goals. But the physics does say one thing that is worth sitting with. Enceladus is there right now. Its plumes are erupting right now. Water from its ocean rising into space, carrying whatever chemistry is in that ocean, cooling and freezing and raining back down onto the South Polar surface. If that ocean contains life, the organisms in it are living right now. They have been living for as long as the ocean has existed, perhaps hundreds of millions of years, perhaps longer. They know nothing of Earth, nothing of the civilization that is slowly developing the capability to visit their world, nothing of the question their existence would answer. And the answer, whether they exist or not, would be the most consequential scientific fact ever discovered by human beings. It would tell us something fundamental about the universe we inhabit, about whether life is a cosmic phenomenon or an earthly accident, about whether the universe is inhabited or empty, about whether we are alone. That answer is sitting in an ocean beneath the ice of a moon 1.4 billion kilometers away. It has been there for millions of years. It will be there for millions more. The universe is patient. It does not require us to go now. It does not require us to go at all. But we might want to, because the question is worth asking. Because some questions are worth the cost of asking them. Because the most important things humanity has ever learned about its place in the universe, that the Earth is not the center, that the Sun is one of billions of stars, that life evolved from simpler forms, that the universe began in a hot, dense state and has been expanding ever since. All of these required someone to look at what the evidence said, however uncomfortable, however costly, and accept it. The evidence from Enceladus is saying something. The water, the organics, the hydrogen, the hydrothermal activity. Something is going on beneath that ice. Finding out what requires going there. Anyone who goes to Saturn may never come back. The rings are worth it. Enceladus is worth it. The answer, whatever it is worth it. That is the specific calculation that the first Saturn crew will make, in full knowledge of the physics, in full knowledge of the cost, in full knowledge of what waits at the other end of 1.4 billion kilometers of cold, dark space. And they will go anyway. Because some things are worth going for, even if you cannot come back. That is what Saturn is. That is why Saturn matters. That is why the most extraordinary journey in human history is worth taking, even by people who understand perfectly clearly that they may never complete it. The rings are real. Enceladus is real. The ocean is real. The question is real. The rest is physics and courage, and the specific human willingness to go somewhere no one has ever been, knowing the cost, accepting the risk, carrying the question, into the dark, toward the rings.